My name is Mike Collier. I'll be speaking today on electric battery management and the need for that. To start off with, we will look at lead-acid batteries and their composition. As you can see in the lead-acid battery at the top removed, that there are 6 cells. Each cell is 2 volts and they provide 12 volts of power. Systems that charge these can only look at the outside voltage, that 12 volts. They can't look at the voltage inside. So if a 2-volt cell is out of sync with the other cells, maybe that 2-volt cell is at 2.5 volts when the others are at 2.3. It can become out of sync and ultimately damage the battery. Battery management for lead acid involves a watering system. As you can see in this little picture, there's a pump. It checks the water level in the electrolyte and the acidity of that. The manager or user can manually add water or add electrolyte fluid to these batteries to bring them in sync. So this is a battery charging without any kind of management whatsoever, assuming a bottom end balance, which essentially means that all the batteries started out at the lowest possible voltage. As the voltage increases, being that they all charge independent of each other and there's no outside intervention, you can see the cell 1 voltage goes right up to the top for the others. And actually it goes red because it goes over voltage and cooks that one cell and reduces its life. In this case, as a lead acid battery, it would be boiling out the water. In a lithium battery, it would damage the cell. Lithium batteries have a much higher energy density and a higher volatility. Therefore, they need greater management. You can see in this picture that there are several cells stacked up. And if you look really closely, you'll see a white little box on a cell board and a green wire that connects and bridges the terminals of the cell. This is a passive balancing system, which means that as the cell reaches peak, that little resistor, or in this case there's 2 resistors per cell, will kick on and begin bleeding off excess power in the atmosphere to slow that cell's charging and allow the others to catch up, so that all cells can finish the race at the same time. So in a simulation with a passive balancing BMS, you'll see the voltage rises across all the cells. As they reach a certain voltage, the resistor kicks on and starts dumping energy in the atmosphere. Now, it's not 100% effective. It can't actually stop a cell from overcharging, as we illustrate how in cell 1, it goes just a hair over that 3.6 volt threshold for that single cell. It's passive, it's wasteful, it bleeds off energy to the atmosphere, and it's not very efficient, but it's very popular at the moment. So the topology. What you saw before was a distributed BMS system. That essentially means there's a single little cell board on every cell. That way when each individual cell goes over or goes near their peak voltage, they will start shunting off excess power. The cells don't talk to each other, but they do pass through a signal to a master control board. But the master control board really has no influence over the individual cells. Its ability is strictly restricted to turning off a charger, turning on a charger, sending alerts, but the cells are independent, essentially. This enables the charger to watch the outside voltage of the pack. In a modular system, there are groups of cells that are managed and watched by slave systems. This enables you to have a pack located in different parts of a vehicle or a system, and each of the slaves then report to a main master control. The master control has a little more functionality. It can turn off or send alert from a specific set of batteries without having to shut off the whole pack. In a centralized system, there's a single board with wires running out to every single cell. It is able to actually check on each cell. It can passively activate the resistive load during the charging process, and it will enable greater control and information from the battery system to the operator or the user. The one drawback is the length of the wires. The resistance of that can affect the readout of the central control board. This system is typically more expensive in a large format. Here in this picture, you can see the evolution of that central control. It's a single board. Everything is integrated into a single plane. All electronics, the circuit flow of electricity. There is still some bleed off in the back on those FETs that you can see on that rise heatsink. Under an active balancing simulation, as the cells charge, the BMS will look to see what the highest cell is and divert power to the weaker cells. This also works in reverse. In a discharge situation, the cells that reach the bottom first will receive power from other cells that have more in it. You can see in the simulation, all cells finish ultimately at the same time. No cell goes over peak. No cell can go over peak. An active balancing control board can actually shut off power in the event of a dead short. There are many types of energy sources. Capacitors, fuel cells, batteries, and they all have different applications and benefits in terms of cost and energy density. The active balancing cell board is able to integrate between all of these, really any actual energy source. It could even be solar, and route power where power is weakest, and reduce power where power is strongest, and balance out any system. The active balancing evolution of electronic battery management is the future of any energy storage, energy usage application, and will enable vehicles and homes and portable power packs to last longer, provide more power over a longer duration. The cycle life of those batteries will last longer or greater cycles because they're not being punished or pushed. A pack is really only as good as its weakest cell. With active balancing, your pack is as good as the entire pack.